To the friction lab. If you remember, we had our dual range force sensor. We're pulling our masses along on our wooden block, and we were taking down some data. So I'm going to show you some sample data and then show you what some of the conclusions are in terms of coefficient of friction. So I'm just going to make up some numbers here. Of course, the mass of the wooden block would have been different for everyone. Let's say, we always want to do these things in kilograms. So I'm going to say that my mass of my wooden block was 0.2 kilograms, and then that means that my total mass was 2.2 kilograms, and if I want to find the weight of that, that's going to be 22 newtons. Remember, we have our formula, which is force of gravity is going to be mass times g. So we always want to remember to put things in kilograms, so they end up in newtons down here. That's going to be our total weight. And then we had some different surfaces over here. Maybe you did something like the table, and you got some different values for your peak static friction. I don't know, 6, 7, and 8, and then this was 7 newtons. Should label these as newtons. And then you got some values for your mean kinetic friction. Maybe it was 5, 6, and 4, and then this turned out to be an average of 5 newtons. Just making up easy numbers. So we want to look at our average peak static friction and our average mean kinetic friction right there for any particular surface. Down here I was asking about coefficient of friction, and I didn't exactly say the right thing down here. I said the friction force is always some fraction of the weight. It's not always actually true that that's the case. It's true if you're on a flat surface, but it turns out to not be true if you are on a ramp or an angle, or and I should say, and there's no other forces happening. So I'll show you what really is happening in a minute. I'll go over it's the same thing down here when I said divide the friction force by the total weight, and that works fine here, but it doesn't work in all situations. But just for example, so you can see what's happening here, if this was my table, my coefficient of static friction is going to be 7 newtons divided by 22 newtons. So we get 7 newtons divided by 22 newtons, and then my coefficient of kinetic friction is going to be 5 newtons divided by 22 newtons. So we can do these here also. 7 divided by 22 and 5 divided by 22. So we get a 0.3 and a 0.22. This is 0.3 and this is 0.23. That equals right there. These numbers right here, the coefficient of kinetic and static friction, sort of tell you how sticky or not sticky a substance can be. They're usually between 0 and 1, and the greater the coefficient of friction, then the stickier a substance is. So that's going to be a coefficient of friction. It's just a value for a particular substance. You can't tell what the coefficient of friction for something is going to be just by looking at it. You actually have to pull on it and have it slide across the surface. And it turns out to be, it's not just the table, it's the table and the wood combination. So it takes a combination of two materials to make a coefficient of friction. Say the wood against the paper, the pen against the wood. You've got different things that are going to slide past each other or try to stick to each other and have different coefficients of friction. So let's move this stuff out of the way, and I want to talk to you all about coefficient of friction over here as well. So let's talk about coefficient of friction. First of all, it's a long thing to write out, and there is a shorthand way to write coefficient of friction, and it's a Greek letter, and this Greek letter is the Greek letter mu, and mu is the coefficient of friction. The coefficient of friction describes how sticky or slippery a substance is. How sticky / slippery. It's really between two materials. So it's the interaction between two materials, and it's how sticky or slippery it is. There's a definition for how you can find coefficient of friction. First of all, I want to mention that there's actually two coefficients of friction. There's a mu s and there's a mu k. And of course, this is going to be a static coefficient of friction, and this is going to be a kinetic coefficient of friction. Usually, the static is going to be more than the kinetic. So generally, you have this kind of situation. Occasionally, you'll have a coefficient of friction, static friction, that'll equal the coefficient of kinetic friction. That can happen. Almost never will you have the kinetic friction be greater than the static friction. What that means is that if you are trying to push a heavy box across a surface and you're putting an applied force on it over here, to get the box moving is actually always a little bit harder than to keep it moving at a constant speed. So just to get the box moving, you have to overcome the static friction force. And to keep it moving, then you have to get the kinetic friction force. So this is an okay diagram. What's better is to draw a free body diagram of the situation. So when we draw a free body diagram of our lab, what we have, of course, we have gravity going down, Fg. We have a normal force going up like this. We had some sort of applied force over here, and then we had a friction force going that way. Because in our lab, I'll move that up a little bit, because in our lab everything was always in equilibrium, when we had the block that was stationary, then we had equilibrium. When we had the block sliding, I told you to make sure you slide it at a constant speed, and that's also equilibrium. Remember, equilibrium doesn't mean necessarily that you're not moving, it just means that you're not accelerating. So it was always in equilibrium, so the free body diagram was the same whether you were moving or not moving. The values of the applied force and the friction force were going to change. So what we saw was that when your applied force, when the block wasn't moving, your applied force had to be a little bit bigger, which means that your friction force had to be a little bit bigger. Back in this diagram, this data table over here, when you entered in the peak static friction and things like this from your graphs, technically what you were actually adding in was what was the applied force. How much were you pulling on the force sensor? But if you look over at our free body diagram, what you're pulling on the force sensor, that's the applied force, happens to exactly be the friction force as long as you're in equilibrium. So if you're in equilibrium, this force is going to balance out this force, and then you can just figure out the friction force from the applied force. Technically, you're measuring the applied force, and we're saying it's equal to the friction force. So that's how this works for a free body diagram. Let me move this out of the way, and I'll show you what this equation is for calculating what the coefficient of friction is based upon other things. And I said that it was over here that it had to do with the fraction of the weight. It turns out to not exactly be the case. So if you want to find the coefficient of friction, whether it's static or kinetic, rather than some fraction of the weight, it's actually going to be a fraction of the normal force like this. So it's going to be the normal force. I think I got that wrong. The coefficient of friction is going to be the friction force divided by the normal force. I had a little moment of panic there when things weren't working out, but I had to think about it for a moment. So if you want to find the coefficient of friction, you take the friction force divided by the normal force. Well, let's look back over at our free body diagram. And in our free body diagram, well, it turns out in our situation, the normal force was equal to gravity because we didn't have any other forces going in this up and down direction. That's not always the case. The normal force doesn't always equal gravity, but in our case it did. That's why I was able to say in the lab over here that it was some fraction of the weight. Remember, the weight is the force of gravity. So in this situation, it's true that you could have used weight, but in general, this is actually a better way to write what the definition of coefficient of friction is. Of course, you can write the coefficient of static friction would be your static friction force divided by the normal force. Or your coefficient of kinetic friction could be your kinetic friction force divided by the normal force. Sometimes it's nice to put a little comma in there. A more standard way to write this formula, and that's why I had to hesitate for a minute, is actually writing the friction force as a product of the coefficient of friction and the normal force. So if you're doing problems and you're given the coefficient of friction and you're given the normal force, you can actually calculate what the friction force is going to be. And I have a video that I'll post for you on how to work problems that have to deal with friction forces as well. So this was the wrap up for the lab. The idea was finding out, one thing was that our peak static friction was generally bigger than our kinetic friction, that our coefficient of friction, static, is usually bigger than kinetic, and then just following up and understanding what coefficient of friction actually means. Hopefully that helps you, and be sure to check out the other videos that I will post.